Good evening. So I'm from Group 3J, and our project is about integrated cooling system of Proton Saga 1.3 liter engine. So I'm Hisham Azbai Fuadi Muhammad Azmi. I will introduce you about our project. So our project is based on radiator and a cooling system. So radiator and cooling system mostly used in every system that has engine, which is combustion system. So this radiator system is used to cool the engine before the engine reaches its limit, which is overheat. So the cooling system mostly use coolant such as water to transfer the heat from the engine and will be cooled in the radiator. So this heat transfer will do its job on transferring the heat from the water, hot water, to become the cold water, to be cycled back to the engine so that the water use can be cycled for a long time. So next, this radiator and cooling system consists of fan, and inside the radiator there will be a fin. So this fin is help to improve the cooling, or improve the rate of heat transfer for the cooling. And the fan also help for the airflow, which is convenient for the convection process of the fin. So next, our background. So our background project is about we take mostly on radiator car cooling system. So we know that an old car usually will have problem with their cooling system, which when they travel for a long journey, they will have a problem with overheated engine. This is because the lack of performance from the radiator and its cooling system for the engine. So to overcome this, we propose on making a new and improve the cooling system for car, with specifically for Proton Saga 1.3 liter engine. And we make it for an old car. So the system we made is basically we improve the fins, the fan, the type of fan, the design of the fan, with the distance of the fan from the radiator, and then and mostly focus on fins. And we made up analysis for the fins, thermal analysis, and we made a analysis on the fan for the rate of airflow for each type of fan. So that's it for me.
Assalamualaikum warahmatullahi wabarakatuh. My name is Ahmad Adjan bin Abdul Rashid, MH135. So I would like to continue about the problem statement of our project. So the radiator of Proton Saga 1.3 liter size and material is different compared to different type of other 1.3 liter engine car. So the size and material is different compared to different type of other 1.3 liter engine car, because maybe Proton Saga have smaller size and very cheap on material. Okay, next, this existing Proton Saga engine sometimes overheated due to the radiator not functioning up to the standard expectation. Okay, for the second one, this existing Proton Saga engine sometimes overheat due to the radiator not functioning up to the standard expectation. Okay, I will continue about the objective of the project. So our objective is to develop a new design of Proton Saga 1.3 liter engine cooling system. and also to improve the efficiency of the car engine cooling system by generate a new design of Proton Saga 1.3 liter radiator. For the scope, actually our project is focusing on the radiator system, since the system is the main component in the car engine cooling system. The study scope is involve a Proton Saga 1.3 liter radiator with different compactness. We choose Proton Saga 1.3 liter because the radiator is more small than the other 1.6 liter car or the higher engine.
And good evening, my name is Muhammad Rafizi. I would like to continue our group presentation on the methodology. So based on the final design that we choose, we need to obtain the required tool, material and equipment. After that, we cut the material into desired dimension and we go through the fabrication process, assembly, before we proceed to the calculation of the heat transfer and the compactness of the fin. And based on the analysis, we validate the result, the data of the heat transfer and the compactness until we achieve the target. Then complete our project.
Okay, my name is Muhammad Syahrim Saini bin Mat Syahri. I would like to present you the bill of material to build this project, the radiator of Proton Saga 1.3. First, we need the aluminium film. This we buy from the Tanah Puteh hardware, about 10 meter, which costs RM2 per meter, and the total price is RM20 all. Next, we need some wood to make the frame for this radiator. We buy 12 feet of the radiator, which costs 30 cents per feet, and the total price is RM3.60 that we buy from the supplier Tanah Puteh hardware. Next, the black net behind the radiator is quantity of 0.5 meter, which costs RM6 per meter. We buy from the Kianmi hardware, which just costs RM3. Next, the glue to fix the fin. We use the glue. We buy 2 quantity of glue, which costs RM2 per glue, and the total price is RM4, and we get from the Kianmi hardware also. Next, to frame the radiator, we use the nails, which just cost 50 cents per pack. We got from Kianmi hardware. For the PVC tube, to transfer heat to the fins, we buy 2 meter of PVC tube, with 1 meter of PVC tube costs 80 cents per meter, and the total price is RM1.60, which we get from Kianmi hardware. The other material that we use is scissors, which costs just RM2. Wood saw to cut the wood, which costs RM2, and the hammer to smash the nail up, and also cost RM2. We got 3 of the item I said just now from kedai RM2. That's all.
For the result and discussion on the first improvement in our project, which is on the material, the maximum value for the heat flow rate on the aluminium is 1.36779 times 10 to the power of negative 13 joule per second, while the minimum value is negative 1.98952 times 10 to the power of negative 13 joule per second. Compared to the brass, another option of material, the maximum value of heat flow rate is 1.29674 times 10 to the power of negative 13 joule per second, and the minimum value of heat flow rate for the brass material is negative 2.33058 times 10 to the power of negative 13 joule per second. Next is the copper, which is the material that we use in our project. If we look at the maximum value of heat flow rate for the copper, it shows that the maximum value is 1.06297 times 10 to the power of negative 12 joule per second, while the minimum value is negative 4.85538 times 10 to the power of negative 13 joule per second. So if we compare between these three materials, it shows that the copper is it gives the good result in the heat flow rate. That's why we choose the copper as the fin radiator. Okay, now I would like to present about the physical properties of the material, which is copper, that we use in the design, fin design. And firstly, for the pure copper, physical properties, boiling point for copper is 2567 degrees Celsius. The density at 20 degrees of Celsius is 8.96 gram per centimeter cube. Melting point for the copper is 1083 degrees Celsius. For the electrical properties for copper, pure copper, the electrical resistivity at 20 degrees of Celsius is 1.69 mu, and the cold junction at 0 degree of Celsius and hot junction at 100 degree of Celsius is plus 76 millivolt. And for the temperature coefficient at 0 to 100 degree of Celsius is 0.0043 Kelvin. While for the thermal properties for pure copper, latent heat of evaporation is 4769 joule per gram. Latent heat of fusion is 205 joule per gram. Linear expansion coefficient at 0 to 100 degree of Celsius is 17 to the power of negative 6, and specific heat at 25 degree of Celsius is 385 joule per kilogram Kelvin. And the thermal conductivity, which is very important in our project, for pure copper at 0 to 100 degree Celsius is 401 watt per meter Kelvin.
For the second improvement, so it is 18 fin is the current design, so we get the maximum value for the heat flow rate is 1.034 times 10 negative 12 joule per second, and the minimum is negative 5.7769 times 10 negative 13. Next, after we improve it to the 20 fin, we get the maximum heat flow rate is 1.06 times 10 negative 12 joule per second, and the minimum is negative 4.85 times exponent negative 13 joule per second. So we get the maximum number is more larger, so we choose the 20 fin as our fin for our product.
The next improvement is the compactness ratio of the radiator. When we increase the surface area of the radiator, including weight, length and height, we will get the more efficient radiator. To prove the hypothesis, we use the compactness ratio formula, which is compactness ratio equal to total area over volume, where total area equal to AT equal to A times TF times 2, both side upper and lower surface. The volume is H times W times D. Total area for one piece of logo fin equal to A R times D. TF equal to TK times TR equal to total level fin. TK is total level fin in one row. TR is total row. R is distance between tube to tube. We put the dimension of our radiator to the formula, and we can get the best compactness ratio for the radiator. The best compactness ratio we will put in to design our radiator for our product. Okay, so for the improvement of the fan for our cooling system, there is 3 factors that affect the design of the fan. First factor is the distance of the fan with the radiator and the pitch angle of the fan blades, and the next lastly, and the next one is the blade tip clearance for the blade. So we have made an analysis for the design of our fan. So from the analysis we made, we found that the best and the optimal blade design is with the distance from the radiator and the fan is 1 inches, and the pitch angle is the best at 27 degrees, and the blade clearance is best at 1 inches. So we for our fan we will choose this value for our best design for the fan. So from all this analysis and model we have done and research we have done, we can conclude that our project can be continued with the product. So for Proton Saga 1.3 liter engine, so we get the improved result from the fan design, the radiator system, the cooling, the heat transfer value for the radiator and the material used for our design. So this is best result compared to the old 1.3 liter engine cooling system.